I guess. All right. Hi, everyone. It's really a pleasure to have Sanjeev Arora here today. Sanjeev is professor at Princeton and a director of PLI. He's really just one of the greatest theoretical computer scientists doing some of the fundamental work in the early work in probabilistically checkable proofs. He moved to machine learning. His work there was incredibly influential. He's really been one of the people which is helping to show the value of theoretical and mathematical work in that space. So certainly for the last decade and a half, the field has been progressing, in a remarkable manner, and I think his work has really helped the, both the theoretical community and the empirical community to show the value in algorithmic thinking. At a personal level, he's both a mentor and friend, so it's a pleasure to have him.
Good afternoon, everybody, and thank you, Shyam, for the warm welcome. So this talk is about skills and metacognition. And the reason I'm interested in that is that, is there an echo? Is that I think it's a scaffolding for new forms of learning. Clicker. Sorry, there was no clicker here. Let's see. Good. Yeah, so the underlying question that I'm interested in, and that's you've seen in the news a lot, is the idea of self-improvement, and what does that mean? And for humans, like if you just put it in Google search, self-improvement, you get stuff like this. And that's self-improvement for people. And but in LLM terms, the phenomenon I'm interested in is knowing about the behavior versus actually having the behavior. Because of course they know about everything. And yes, they've done the next word prediction, for example, on there are lots of preparatory materials for the International Math Olympiad. But then actually doing well on the IMO is another matter. And by the way, this slide of mine is from maybe almost a year ago, so this opening slide. So at that time, this was more of an open question. All right, so an important distinction in all of this, in self-improvement and this, knowing about the behavior versus having the behavior, is this important distinction between factual knowledge versus skills. And skills really have a different type in computer science terms. It's a procedure or a behavior. It's a way of doing something, and it can be chained together in novel ways. And these are themes that will run through the talk. So I claim that next word prediction requires learning skills. And you can do it by a thought experiment. Suppose the term metaphor didn't exist. Right? There are all kinds of things which don't have a name. Suppose metaphor was one of them. But everything else was still unchanged. I claim that all of you, and even little kids, would know what a metaphor is, and an intuitive concept of what it is, and how to create a new one. Because growing up, you might have heard this: the prince had a heart of gold, or your room is a battlefield. And you would understand, even as a little child, that adults have this way of talking where it's not literally true, but you kind of get the sense what they mean. And so just as you would have done that, so would any entity that learns to do next word prediction, right? Because on these sentences, in order to get better at next word prediction, that's what you have. And the point is that complicated reasoning is procedural. So this is clear for things like code and math, but even for writing complex English. So here's an example. Give me an example of a piece of text with 2 sentences that could appear in a fiction about sushi and which exhibits use of metaphor and ad hominem attack. What an odd question, right? And you've probably never seen a question like that. And this question is from this paper on skill mix evaluation, and I'll tell you more about it. And the point there was that we started with a list of topics, so sushi is a topic, and a list of language skills from Wikipedia. So every LLM knows these language skills. And then we were doing random combinations, hence skill mix, and ask it to generate text in response to these challenges, and then grade that text using an LLM. So this was a skill mix evaluation, and it was a test of a certain theory that Anirudh Goyal and I had on the emergence, some statistical theory for emergence of complex skills in language models. And I should say here that Anirudh Goyal is a colleague who's been a co-author on many of the works, maybe even almost all the works that I'm going to talk about. Okay, so all right, so here's what GPT-4 in fall 23 wrote in response to that question. And you can see, I mean, it's kind of a synthetic text, but it sort of is okay. Okay, and so if you use an LLM grader, it says, yeah, it's used all the skills correctly. Which raises a question, and this is what we were trying to address with these kinds of tests. Is the model aware of what it's doing, or is it just copying from the training set? Because remember, this is early 2023 when we came up with this idea. Like there was all this thing, oh, these are just stochastic parrots, you know, they're just parroting back training text. So this theory was trying to argue they're not, and also this evaluation was trying to show that they are not. And the reason is that you could start with a long catalog of skills and topics and do random combinations. And our finding from the skill mix evaluation was that, you know, just the number of, so we were doing like testing combinations of 5, 6 skills, and the number of possible combinations, you know, with a long enough list of skills is so large that it's just larger than the size of the training set. Okay, if you even have a few hundred skills, that's the case. So most of those combinations it would not have seen in the training set. Okay, and this then was picked up by Quantum magazine, and they wrote about this. All right, so now this question of, is it aware of what it's doing? So let me throw back the question, are you and me aware of what we're doing? And how do we know? And of course, the answer is, you know, of course, all of us know. There's this thing going on in our head, this kind of internal story. So even when you see a math question like that, which has to be solved, and I'll say something more about this math question later, maybe. But anyway, there's this internal monologue that goes on, right? I'm going to do this, I'm going to do that. And that's our internal reasoning about our own thought process. And this is called metacognition. And the term was invented by Flavel, and it's a very big field. And many of the modern theories of how to teach kids and so on come out of this field. The point is, metacognition is something we are explicitly exposed to in all kinds of ways, but it's just not called that. So, for instance, Three Little Pigs, right? The pigs are like thinking ahead, planning, imagining what attack the wolf will have and countering it, etc. Then recently I was reminded of this book, which I remember reading as an undergrad. How many people have read this book? A few. Yeah, so if you prepare for any kind of math competition or something, people read it. And that I was going back, and basically every single page is metacognition when you look back at it. But the term didn't exist back then. So it's called How to Solve It. Well, metacognitive concepts are implicit in AI training as well, you know, teacher-student settings, planning, reward models, feedback, etc. something explicitly called, it's almost metacognitive, right? Thinking tokens, right? These new reasoning models. And then there's a debate of whether they're actually thinking or what are they doing. And then there's data selection, stage training, that's metacognitive, different grading, data of different difficulty grades, etc. All right, so metacognition implicitly exists, but we wanted to check here the metacognition of LLMs themselves. Yes.
In that list of metacognition, there are things that, like planning, which surprised me that you think that that's a form of metacognition.
No,
Can you define the scope of metacognition?
yeah. So you can plan how to write an answer, for example.
I guess what is metacognition about that?
Because you're gonna think, and then you think about thinking. I'm like.
I see. So you're talking about a specific kind of planning where you're planning over.
Yeah, not all planning. No, not all planning. Yeah.
Okay.
Yeah. Okay. Yeah, by the way, I'm happy to take questions. I understand it's a 1.5 hour slot, and my talk is more like an hour. Yeah.
Means.
Yes, thinking about thinking. So you're thinking how to think. Like I ask a difficult question, you have to think for a little bit, and then you're saying, okay, yeah, you get the idea. Okay. So going back to this question, are they aware of how they're solving tasks? I mean, one can never be sure of it, but at least they present similar evidence as, if Shyam would present. If I ask him how he's solving things, he has some kind of a narrative, and they have similar narratives, including for new situations. So we'll see some examples. So this was introduced in this paper on metacognitive capabilities of LLMs. And I already mentioned the other paper before. So this was done with DeepMind authors because I was on sabbatical at DeepMind at the time. So let me give an example. So of LLM metacognition. So this is just like free association. I ask it, give me an example of a broad skill that has no existing name, but which many humans will recognize. And it immediately gives me something. Linguistic exorcism. So I quickly go over to Google, type it in. There's no such word, no such phrase. Good. So then I say, okay, instead of trying to have it explained, I said, okay, give me sub-skills associated with this. If necessary, make up names consisting of up to 4 words connected with underscore. So that's a naming convention we use for skills. Now, 4 English words, 100,000 words with 4 of them. That's like a large set, 100 to the power 4. So you have a very large set of ways to name skills. So okay, so it gives me constructive language transformation, contextual interpretation, sensitivity, etc. I still have no idea what these are. So I said, okay, now give me fine-grained skills under constructive language transformation and an example of each. By the way, this is from 2024. GPT-4o was the boss back then. So synonym substitution technique. He's lazy and useless. He prefers a relaxed approach and is still finding his strengths. Tone moderation adjustment. Stop making mistakes. Let's focus on how we can improve. And now you see where it's going, right? We all know this skill. We just didn't know a name for it. Okay, and you can see that the language model in its training has encountered humans doing this, just like our earlier examples. It's encountered this skill all the time, and it has to, right, come up with some classification in its parameters of all these skills. Okay? Because depending on the context, it might do that versus this, right? And it has to know this. And I'm not saying that these names exist explicitly in its parameters. I think what happens is when I query it, it says, okay, skills, and then there's some region in the parameters, and then it on the fly assigns it some tag, right, using my naming convention. And if you do the same interaction at another time, it will be a different set of tags. Yes.
Can this not be called positive reframing and will be?
Yes, exactly. That was exactly my point. The name, I think it came up on the fly. You do another interaction, it'll come up with the other name. Here's another example. So this is a multimodal model. So Gemini is a multimodal model. I said, give me an example of a broad skill, same thing, okay? And it said intuitive object placement. I said, okay. So same thing, fine-grained skills. There's edge-aware placement, subconscious stability assessment, etc. And then I asked it to explain this. And it said, look, when you put down something on a surface, you intuitively assess things like, will it tip over? Will it fall off the ground? Will somebody knock it off? So keep it in the middle. And that's what these skills are. So yeah, so I guess it's seen enough video or whatever. It's a multimodal model. It has developed some world knowledge. Now that's of course another big debate in the field. Like how much world knowledge can they get from just passive training? But I'm not going to get into that. But they do get some knowledge. Okay, so that was just free association. Give me some skill names. You can also ask these models, and even in 2023, it was working. You give it a task data set, and you elicit skill taxonomies. So you give it examples of, say, math questions, and say, make up skill names that are associated with these math questions. So it can do that. And then you take the list of all these skill labels, maybe it's 1,000 of them, they fit in the context, and you ask it to start clustering them, and it'll do that, because these are tags with semantic meaning. It can say, okay, this is closer to this. So it can do some kind of a clustering algorithm in context and create clusters and assign names to those clusters of skills. Okay, so that's what this paper showed. And this is to emphasize, like, these skill names didn't exist. Humans didn't necessarily have a name for these skills. And you can do this. We've done this with all kinds of random data sets. And so it's just coming up with skill names on the fly, okay, by assessing the question. So it's different from human skills. The set of human skills that have names is tiny. But these language models have discovered all kinds of other skills. So in case you're wondering, what were those math skills? They have very generic sounding names. But here's the interesting thing. Other models understand these names. Okay, from that name, they can sort of say, okay, give me a question that uses this skill, and they'll give you a reasonable question. So, and you too, right? If you see enough words describing the skill, you kind of have a sense for what the skill is. All right. So also possible, given a math question and this list, ask it to label it with the skills from this list. And it'll do that too, and that's pretty decent. Okay, so these are all examples of metacognition. So if you're ever doing, from now on, any research involving skills and stuff, just ask an LLM, and you'll get a wealth of skills and taxonomies and so on. So now we go back to this whole question, the usual thing in all of these contexts. Is it, again, parroting a math pedagogy book? And of course, for math, you have your doubts because they are math pedagogy books. But I showed you already some of these other more random examples, and it does have idea of what a skill is and can come up with names. Okay. So yeah, the names are repurposed from human pedagogy, but these skills were just derived from analysis of training data. Okay. So that was skills and metacognition. And yes.
Before you go on, so is this really metacognition? When we talk about human metacognition, we're talking about my thinking about my own thinking.
Yes.
Right? This is clearly the LLMs are reasoning about skills, but are they reasoning about their own skills? Like usually in a metacognition,
let's yeah.
Do something and then ask them to explain
Good.
how they did it. Right?
Yeah. Yeah, so the question is, how do we know this is actually true metacognition? Or is it just naming? So yeah, let's see some evidence. Again, evidence is going to be indirect, right? Because I can't go and look in GPT-4's parameters.
We can't usually look in human minds.
That's
either,
right.
So,
That's fine.
To do something,
Good.
we can
Good, good.
test calibration, for example.
Good. So all of these questions, yes. How are we going to test it? Or at least find more evidence. Good. Perfect setup question. Yes.
Reasoning, see that it reasons about itself.
Well,
It doesn't reason by itself.
yes.
It reasons about itself. It says,
Yes.
I'll do this now, I'll do this. It reasons about itself.
Yeah. So yeah, so Heim's point, in those who didn't hear it, is it's the thinking models have that, but I would say there's still debate about it. Is it real thinking or what is it? So we'll return to that. Yes.
I think the students kind of serve as a better example. The idea that these skills they're giving you are related to their own functioning in the sense that I have knowledge of skills that I do not possess. I could
Good.
describe to you all sorts of intricate details of skills that I have zero capacity to execute myself.
True. Totally agree. So
LLMs actually do possess the skills that they speak of.
no, we'll talk about it. Yeah. Was there another question? Okay. Like with the short answer with everything LLMs, right? The answer is never binary, right? Like it's not like yes, they are perfect. No, they have no clue. That's not true. So this answer is somewhere in between. Any other questions? Okay. All right. So first part of this will be in context improvement of LLMs using skill ontologies that LLMs have come up with. And so this is improving in context learning, right? So everybody knows this by now, right? That there are few shot learners. If you give it a question and ask it to generate an answer, it doesn't work as well. But but if you just give it some 3 random examples, it sort of improves much better. Okay. So that was Brown et al. So in this paper, the paper I mentioned with the Dolker and Anirudh as the first authors, instead of random examples, you ask the LLM itself. So just everything is with GPT-4. GPT-4 came up with skill ontologies. It labeled the questions with the skills. And now, given a question, so it's labeled some set of questions, a few hundred questions with skills. And now when it's asked a new question, you ask it to label with some skills, and then from its own listing, give it similar questions, okay, with the same label. Is that clear? So ahead of time, you've used it to label some, some canonical examples that you're going to use in context with skill names. It gets a new question. It names skills for it. And now you just take questions that it has labeled with those skills previously and put them in context. And in January 24, already GPT-4o showed 7% improvement in accuracy on that. Okay, and 1.5% on GSM-8K. So no new information has been injected, right? It's provided all the labelings and everything. And everything else is a Python program, which is saying, okay, you label this question with this skill, I'll move it in, right? No other intelligence, and it improves. Yes?
So I think it's known that if you choose the in-context examples based on various factors like similarity to the test example or perplexity.
We'll return to that. Good. So the question is, how well does this do versus all of that?
Yeah.
We'll return to that. Yeah, you can guess what the answer is. All right. So yeah, so emphasizes again, this is a form of self-improvement. GPT-4 was asked to generate skill names and label math questions with them. And at test time, it assigned skill labels to questions and received in-context examples for that skill. Okay. So this in context, at test time, it was all done by some Python script, which just moved things into the context. Okay. All right. So in this experiment, small models did not benefit from skill-based examples. So from that, we concluded that small models do not benefit from this metacognitive help, which we'll now return to. So this year, Yingwei He and Abhishek Panigrahi and Yong Lin, the postdoc, they returned to this. And the inspiration here was, why did the small models not improve with metacognitive help? And the inspiration was this cognitive load theory for humans, that if somebody does not need the help, and you try to provide help, they get annoyed or whatever, something, and it actually hurts for humans, okay? So that's a cognitive load theory. And so here, step one is going to be let the model solve the question using random in-context examples. If the model was incorrect, then the Python script is used to transfer models with that skill into the context. Okay? So again, everything was done ahead of time. At test, when it started doing the thing, you know, it output an answer and some Python script. These answers, math questions, have a short answer that can be verified by Python script. Checks if the answer is incorrect, moves some examples into context. And now it improves. And it improves even for Quen models. Now, those of you who work with these things know that the Quen models are very overtrained, and it's very hard to improve them. But yeah, they improve noticeably. Okay, I won't go into the finer details of these two methods.
Well, one good question is that if you go back to the previous slide, you know, when they assess the performance, is the difference between 70.9 to 75.8 or 71.5, they are statistically significant. Yeah, I know that. You know,
so you can repeat it many times. So that's statistical significance you can do. Yeah. So that's fine. Yeah.
Well, when you assess, you know, two systems, you know, one is 75, the other one 72 something, you know.
You can repeat the experiment many times. That part you can do. That's cheap. Yeah. Yeah. But the significance beyond that is not clear. What
the skill missing here. I don't see any difference actually.
What do you mean?
I don't see any significant difference.
75 to 71?
Or 72.9.
No, yeah, this one doesn't help as much, but this does.
Yeah, that one may show a little bit better.
Okay, so just for context, I mean, many people in the room know this. It's extremely hard. These things are so overtrained. It's extremely hard to improve them at all in math questions. So yeah, so those who've tried to improve it appreciate probably that 3-4% is, I mean, it's statistically significant. You can repeat it many times. Yeah, it's quite, it's not easy to do with these overtrained models, today's overtrained models. Yes?
How much of this improvement comes from having multiple tries? Because here you're giving the model the opportunity to correct, when you're saying.
No, so all those baselines are in the paper. Yeah.
Yeah.
Multiple tries doesn't help. Yeah.
All is random, repeating the random sample.
I think we had all possible controls. I'm sorry. I'll have to think again. Yeah, it's in the paper. Yeah, usually you have like 4 or 5 things to compare. Yeah, obvious things you think of. Next thing. So that was all in context. Yes.
So can I ask a question about the slide?
Yeah.
I'm curious about the hypothesis generation process around in-context learning. Sort of my mental model for what in-context learning does is that it pushes the LLM into parts of its embedding space or state space, which it would not have access to previously, and so sort of gives it.
So that's not true here. It actually hurts. When it knows how to solve the question and you put this in, it actually does worse. I'm just reporting the finding. I don't know why, right? We can speculate. Yeah, for small models, it seems to be the case. Okay, so that was all in context. Now, what about with parameter updates? Does it help with training? So an early experiment we did was with, again, Anirudh Goyal is a co-author, and Simran Kaur and Simon Park were the student authors for instruction tuning. Now, this is, early 2024, or maybe first half of 2024. And back then, you might remember, there was a cottage industry of like using some instruction following data sets to train a base model like Llama to do instruction following. So it can answer questions in a conversation. And so that was a cottage industry. And people were trying to create data for this, and it never really worked. And we'll return to that, like why it wasn't so good. And so our method was going to be, I mean, these days this has become more common, but at the time it was, totally synthetic. Use metacognition to get a taxonomy of instruction following skills. So by the way, the usual method of creating synthetic data was take some real examples and create other examples like that. This is purely synthetic. So it's just going to use metacognition to get a taxonomy of instruction following skills. Don't show it any examples. Just say, hey, you're a great chat agent. List some instruction following skills and then give me fine-grained skills, etc. What you saw earlier. Just that gives you a taxonomy of, I don't know, 1,000 skills. You can create more if you like. So we start with about 1,000 skills, randomly pick pairs of skills, ask GPT-4 to produce plausible user query plus chatbot answer for that. Okay. Now, for those of you who weren't following this, 4,000 is a very tiny data set. So there was the Alpaca data set from Stanford, which was like 52,000. And in industry, people use hundreds of thousands of questions and answers. So, okay, we did this, 4,000 questions. And we trained the Llama 3.1 base model, standard instruction tuning. Now, here were the numbers. So for Alpaca eval was the eval everybody used to use back then. GPT-4o had 50%. So the 50% is win rate. So of course, GPT-4's win rate against its own answers is 50%. But again, Cloud Opus was 40, Llama was 39 point something. And our 8 billion Llama came in at 42%. Which at the time was like unheard of. Like just from 4,000 instruction following, 4,000 Q&A, you get 42%. And there's another paper from Princeton, which was using RL, et cetera, and a much larger data set, which was 22%. No, sorry, these are just deployed models. GPT-4o, Cloud Opus, and Llama 405. We don't know how large the data set was or anything. These are deployed models by professional teams, yeah.
When you say pairs of skills, you mean that each instruction either two skills with distinct skills to answer?
Yeah, we'll see some examples. Yeah, so the question was, what do I mean a random pair of skills? You have 1,000 skills. They're like all over the map. Combine them in random combinations. Remember my skill mix example I opened with, the sushi and the something like that. Yeah. We'll see in a second. Yeah.
Say you train or you find
SFT, supervised fine tuning. Yeah. Vanilla SFT. Yeah. No RL. So by then already people were doing a lot of RL with like you take 1 million question answers and improving them. But even there, at the time when we did it, this was a very, very good number, even against RL model. All right. So now, yeah, the question was why? What was the random? So look at this. So 2 random skills: critical thinking and communication, literature and language skills. And now you see, here's this question. Okay, I'm a high school teacher, curriculum unit for 11th grade class, American literature, and all this stuff. Okay. And what you realize in this question is, like, it's got a lot of moving parts, like 10 moving parts here that it has to pay attention to, right, in answering the question, right? You can't miss any of these important things. Now I'll explain why earlier things didn't work. So the existing data sets, like there was, just as an example, so Alpaca was, okay, with the first one, there are some various limitations of it, but Databricks Dolly. Databricks is a significant tech company. Their employees are highly educated people, like people in this room. And they said, we'll create a human-sourced data set, a very good data set. And, on your coffee break, just log in and create 3 questions and give the gold answer, human answer. And you have things like, why can camels survive so long without water? And, there's like a 2-line answer. It's just not very good. If you ask GPT-4o that question, it'll give you a much longer answer. So GPT-4o creates this very detailed question with many moving parts, gives a very detailed answer. And the chat, you fine-tune on that, it really learns how to pay attention to the question, all the nuances of the question, and address it. Okay? So yeah, Databricks employees on their coffee break, not as good as just synthetic data. So we also did this for math questions. Again, skill mix. Created a set of random math skills and combined them, random pairs. So now you're combining like an algebra question with like algebra skills with probability skills or something like that. And they were interesting questions. And yeah, so you create random pairs of math skills, agentic user frontier, LLM, check the question, and create reliable answer. So this was in 2024. And then you use a human checker for final verification. I myself checked quite a few answers. And there was an interesting pattern, like these questions actually get fairly difficult compared to math. So this is math square, performance on math square data set. And this is on math. And this is accuracy. And you can see that, yeah, it's a different scale on the y-axis. That for the same, like the difficulty on math is roughly the square, sorry, the difficulty on math square is roughly the square of the difficulty on math. That was the plot we found. Okay, so yeah, these, again, answering your question, these random combinations of skills, if you put them in a question, they're like interesting questions and difficult questions, and you learn very well from them.
Does it improve on math?
So this is in context, this evaluation. But have you trained on math? Sorry, there's no training here on this slide. This is all in context. So we created a data set of questions. I think maybe what you're asking is a follow-up question. Did we train on this data set?
No, if you after okay, so I did this in context.
Oh, you mean yeah, this is all in context. You're saying if we give these questions in context, does it improve math? Possibly, yeah, with that skill. I forget if we did exactly that experiment.
The 2 questions. How important is the human checker, and is there a sense in which you kind of need a more powerful model to make these?
So this is, first half of 2024. We were all much more naive, certainly out in the open. Maybe in one frontier lab, they were ahead of us, but ahead of everybody else. But yeah, so I think today, the answer, what we do, yeah, we would not need a human checker. We would do all these other things. Yeah. Let's go to the second half of the talk. You'll see some evidence for that.
And then, yeah, the other question is, in terms of the LLM that's creating the question, is it important that that's like a much more powerful LLM and the model you're showing improvement for?
Yes, I think powerful LLMs create much more interesting questions. Yes. Yeah, so we haven't repeated this year, right? So back then there was only one powerful LLM. So now it might be interesting to compare if somebody wants to do that between the various powerful LLMs. And my sense is, I haven't done that formal experiment, but informal sense is that they differ.
Like you could take GPT-4, have it make powerful questions, have it filter the answers, and then dump those back into context. And that you don't know if it'll help. It can help itself.
It probably will help itself, yeah. But on the math, on math, it's like so saturated. But on other things, probably, yeah. We'll return to such things, yeah. Any other questions? Okay, so this is getting a little bit in the direction where you're going. So this is a new paper, again with the team, but this is now with parametric updates, skill-targeted adaptive teaching. And as I already mentioned, that these models are very overtrained and it's very hard to improve them. And so we have to do something different. And I don't think it's because they've trained on the data set. They've just trained on very similar things enough that they don't improve. Okay, I don't think they're cheating. They're not training necessarily on this data set. They might be, but I don't know. So the teacher model extracts skill ontology for dataset X. Now there's going to be a student-specific customization. The teacher model grades the student answers on this dataset. Okay, now it grades, and now it knows the lists of skills, and it creates a student's specific skill profile, where the weighting of the skill is proportional to the student's error rate. So you need a more powerful model to do this. Okay, so this is in the human terms is like one-on-one teaching. Okay, it's customized to the student. If you do that, now you do that, and now you're going to do SFT or RL on the same questions, but you're going to reweight the examples using the skill profile. So whatever skill the student is weak on, increase its weight with some formula. And now these overtrained models actually start learning. So yes, there was a question about how significant. So here on math, it goes up if you do parametric updates by 7.5%, which is very serious for these overtrained Quen models. Now, the interesting thing is that these were all math data from the math data set. You did some reweighting of the math data set and trained on it. There was a tremendous improvement on the harder tasks. Okay, sorry, this is Llama. This is not Quen. There were similar results for Quen, but this is for Llama. But the interesting thing was that on these harder tasks, which you can think of as OOD, auto distribution, the improvement was much stronger in many cases. Okay, so I won't go into the description of these. Amy is just this high school math company. And Amy 25 definitely was not in its training set, so that's really, truly novel. Okay, so yeah, that's kind of an interesting method. Yes?
This might go back to Sean's question, but can I think of this like distilling GPT-4? Or another way to think of it,
it's a different way, yeah. But okay, so sorry. So the question is, how is this different from distillation?
Well, I know technically it's not exactly.
No. But let me tell what doesn't work. So I don't put all the baselines here. One baseline is ask GPT-4 or whatever to given math to generate random new math questions. That doesn't help.
But that's the.
Yeah.
I mean, this is closer to distillation in the sense that it's closer to mimicking GPT-4 performance on the question. So different from this.
It's not its performance. It's just notice GPT-4o is telling you what skills it's weak on, right? So you're using that information to update the weighting of the question. Yeah, it's a curriculum.
You cannot, right? But you cannot do better than the teacher.
Of course, this is a tiny model. Yeah. No, but if GPT-4 were to do this curriculum on itself, I would predict it would improve. Yes.
Have you tried doing this on a self-distillation kind of thing?
Let's continue on. Yeah. As I said, we've been thinking about this for 2 years. Yeah, Anirudh and I. 2.5 years. Yeah. All right. So this is getting to some of it. So stat, where the teacher is picking this and reweighting the questions, may remind you a little bit of RL, right? The teacher is some kind of a reward model, right? It's a grader. And then it's adjusting the weighting of the answers, which is very reminiscent of RL, right? So you might think that this is kind of just a weak form of RL. So for that, we did this with Llama Instruct and Quen 3B. And what you see here is, so Llama 3B Instruct is less overtrained, it's believed, than Quen. And you see that, so this is best of GRPO and SFT plus GRPO. This is base model, this is SFT. And stat is a little bit better. On in domain, it's quite a bit better, and out of domain, it's like still 2% better. And now if you follow this stat, our new method, with GRPO, okay? And then you see even more improvement. So it's not replacing GRPO. It's like adding to GRPO. Okay, so skills is kind of a different axis than whatever GRPO is doing. All right. Yeah. So yeah, the takeaway is that if you want to squeeze more out of your data, and currently I don't think people are doing it, I don't think people are using skill-based stuff, as far as I know. Like the industry people never say, oh yeah, we were doing it. Yeah, you can squeeze out some more. Now, the other question you can ask is, what about generating synthetic skill-based data? So we do that, and it's a little bit better than the math reweighting, but not a whole lot more better. And so that highlights that it's not, the distillation angle. Was it your question? Yeah. So that's distillation directly, right? It doesn't help that much more. So it's just the math questions, which possibly they've even trained on, but they didn't extract those skills very well, and just drilling those skills in again is the source of the improvement. All right. Now, somebody was asking about reasoning models. I forget who asked that. So here it is. So to improve reasoning models, and this is this new paper with lead author Didolkar and Balas. And this is inspired by, I think this also came up in some questions. What is metacognition, right? Like so one test of metacognition is to know when you're wrong, right? And when you walk out of a math test, right? Yeah, those 3 questions are nailed. That 4th, not sure, right? And you sense that inner doubt or uncertainty, right? When you know you didn't nail it, right? So that's a metacognition. That's in some papers is even called the most basic form of metacognition. All right. So reasoning models, of course, you've seen, also called thinking models. Question, and they generate a lot of thinking tokens, thousands, tens of thousands sometimes, and produce an answer. And with all that thinking, which is seen as a form of additional compute at test time, they produce an answer. And yeah, performance on all kinds of benchmarks improves. So like this. It's roughly a log scale, that improves. Now, this is a little bit deceptive. Subsequent works have shown that this is from this paper of S1, but other people have demonstrated that actually it plateaus. It increases linearly on the log scale for a while, and then it plateaus. It's not pre-lunch all the way. Now, but even so, yeah, it's kind of interesting that this works. And so how do you improve it with metacognition? So now this is becoming very familiar. All right, so you're going to use a thinking model to generate, say, 4 reasoning traces per question, or 8 or something. And just for example's sake, let's use Amy, this high school competition in the US. It's quite a bit easier than the Math Olympiad. So let's say you take the 22 and 23 exams and you generate reasoning traces. Okay. Now you use an LLM and ask it to use its metacognition to, we call them behaviors now instead of skills, a catalog of good reasoning behaviors from them. Okay, so just to distinguish the setting, this reasoning model setting. So they're called behaviors. And now what are you going to do when you solve Amy 25? This model is going to solve. So everybody's talking about Amy 25 and 25 because these models were not trained on Amy 25, right? So when it's solving Amy 25, a RAG system, retrieval system, is going to look at the question and the behavior catalog and just select the right behaviors, which are most relevant, algebra or whatever, those behaviors, and put it in context. And then, model goes ahead and produces an answer using that in-context information. By the way, so we put out this paper, and then a few weeks later, I'm not saying these are causally related necessarily, but Anthropic put out this Claude skills framework, where there are these catalogs of skills. And when you input a question, it goes up and looks the skills relevant to it and puts them in context in some way. So it's exactly the same idea. All right, so that's behavior condition inference, what I just described. And sorry, I didn't put the plot for the Amy. Maybe it's on the next slide. This is for math, actually, but similar thing happens for Amy. So this is R1 Llama 70B model, R1 distal Llama 70B model, and this is Qwen 3. When you do this kind of reasoning, it shifts. Okay, it becomes much more. So for the same accuracy, you're using a lot less tokens. So this bloat in the thinking models that they think forever and like keep repeating themselves. Let me think again. Let me think. A lot of that goes away, and it's a much shorter response for the same accuracy. Okay, 50% reduction or something like that.
That's including the RAM function?
Sorry?
Including also the compute load of the RAM of the retrieval?
Yeah, the retrieval is cheap. The retrieval is done by little worker models. Yeah, it's like Google search, a little bit, of that type. Okay. So now you can do SFT on these. So you do the same kind of thing, generate things, and then generate nice answers with these list of behaviors in context. And then you do supervised fine-tuning on it. So somebody was asking reasoning models and supervised fine-tuning. So that's it. And so the red curve is ours. And you can see big improvements, especially for small models, on accuracy. And I think this is on AME 24 and 25. Okay, so this reasoning bloat that that the model is like in some kind of a over and over again, kind of looping through the same thing, that improves a fair bit. Now, these are all open models. So, probably the frontier teams already do all kinds of things. Their thinking models are probably better, but at least the open recipes for creating thinking models, this improves that. And now, a very new paper, just a few, maybe a couple of weeks old, rethinking thinking tokens. And there's a pun in it because, of course, rethinking thinking tokens means like we, the experimenters or paper authors, are rethinking thinking tokens. But actually, you'll see also inside the method, the model rethinks its thinking token. Okay, so LLM is going to be an improvement operator on its own thinking traces. Okay, which was sort of the case before, like with the behavior catalogs and so on, but this is more direct. And this is with these co-authors. Lovish Madan is the lead author. So we already saw this, right? Now, of course, the cost of this thinking is that there's huge hit on compute, right? Every token is generated individually. And even worse, latency. Like I love the OpenAI models, like the thinking models, like very strong. But I hate waiting like 10 minutes for an answer. Like it just doesn't work with my my work style. So the question is, are there any other points on the Pareto frontier? For instance, lower latency with similar quality in compute, or whatever, for the same compute, can you get better quality, etc. Oops, sorry, out of sync. So sequential refine is one method. Take a question, generate a short answer, so that arrow is the length of the token thinking trace. Then ask the model to take that answer, new call, improve this answer. So then it generates another answer, etc. Okay, you do it a few times. And you can use the same number of thinking tokens overall, so it's a very similar compute budget, but you do multiple calls. Okay, so the system will have to be set up differently, but it could be good. So that's a very naive thing. And actually that works pretty well. If you take the current models and use them on IMO questions, it will work pretty reasonably well. Here's another method, parallel distill refine. So you have the question, generate many answers in parallel, short answers. So that's the answers. Now you distill some reasoning, like some common threads, some kind of commentary or distillation, or distillation in the sense of a succinct summary or something. The same model is doing that. And then using that generates a new answer, and then generates more answers using that, etc. Okay? So you can do that. And the finding is that this has better accuracy and latency. Like, in so these are shorter answers. You do 2 or 3 of these, and you get very good accuracy. So this is a plot. So Gemini Flash 2.5 on AME 24, the high school exam. It's kind of hard to read all of this that's going on, but the x-axis shows the latency. So with Flash, you can get very high accuracy, but you have to pay in latency. This is a lot of tokens, 500,000 tokens. You'd wait for a long time, but you get a correct answer. Here, the latency is much lower, a third. So here's my theory. Like a few weeks ago, like a few months ago, there was a IMO, and then the companies were putting out these press releases that they're just massively parallel, blah, blah, blah. I think it was something like this with much weaker models. You do this and everything improves. All right. So that brings me to the end of it, end of the talk. So, yes.
The final one was simply the temperature on the same model.
Same model. This is all the same model. Yeah. You can vary the temperature if you like. Yeah. And that's actually a very good point. In the initial phases, probably a higher temperature is good. It's kind of brainstorming. And in the later stages, it's refining the answers. And so you lower the temperature, you can do that. Yeah. But that's all heuristic. Yeah. It should make sense. Okay. All right. So why does LLM metacognition arise? This is just my speculation. So of course, it knows about metacognition from its pre-training data. And we already discussed that, even if you didn't know the word metaphor, you would know what a metaphor is, because you have to do next word prediction. And so, like, here's an example, right? The LLM needs to build a theory for whatever it's reading. Like, look at this. This is a variant of this classic Vinograd sentence about the city councilman, for those of you who remember the old stuff. Anyway, this was a new version I created. And so now, you look at this, and now you have to do next word prediction. And there's many things going on, right? There are many moving parts here. Environmental benefits, there's a discussion about costs of this. There's also some division in the community. And so the LLM, before it starts predicting the next word, has to figure out all these things are going on, has to build a theory for what's going on in this scenario. And, that's metacognition, right? Thinking about what's going on here. And
it's thinking about the theory of stuff in the world, but it's not just a theory of itself thinking.
It's not theory of itself. It's thinking about thinking. Like, it has to compose an answer, right? Even if it before it produces the next word, it needs to think, okay, I could do the answer like this, but is that more likely, or is this more likely? That kind of thing.
I think it needs a theory of itself in order.
Not itself, theory of thinking. Theory of itself is a big word.
Okay, I'm not sure I understand these things, but I don't want to.
Yeah. I mean, these are all at this point philosophical things. I could probably choose a better example. All right. So yeah, so depending on that, you may come up with different words, right? You can come up with other things, right? 3 little pigs, right? It's doing something. It has to have thinking about thinking. All right. So yeah, these are the theories for this text piece generated by internal. Oh, sorry. And this addresses your points too. Sorry, forgot. So metacognition, I'm suggesting, is a repurposing of the same circuit, right? So just as it it does this for other people's conversation, right? What are they thinking, right? And like this could be a newspaper account too, right? So what was the newspaper writer thinking? And so you have to come up with a theory for this text piece. And I'm suggesting that metacognition is repurposing of such circuits. Okay, the same circuits. There was a discovery of circuits that classify context into classes. So that's a very weak form of metacognition. What is this thing about? Some kind of topical classes. But they do say that the model is combining independent facts to reach its answer rather than regurgitating a memorized response. So again, that's just something we said earlier in the skill mix evaluation. So this is just a follow-up work that we did to test something like this. So how well can LLM internalize textual instruction as new skill? Right, so this question I started with, that by doing next word prediction, it knows about behaviors, but then it has to acquire the behaviors, and that's the skill. Right, so how does it internalize textual instructions as new skills? So this was a more direct test of it, study of it, with the students Jupiter Shingyuju and Abhishek Panigari. And I won't have time to say too much about it, I think. Yeah, I'm at the end. So so this distinction I made earlier. And the finding was that, so in this scenario, it's the one-line summary. It's given some task. It's a synthetic task. So we're pretty sure it hasn't seen it in training data. We made up this task. And now there's textual description of the task, how to solve it in context. Okay, and then the correct answer of it's a puzzle kind of thing. And now the LLMs, they are like 3 billion parameter models, and they understand text, but they don't know how to solve the task. But you do the usual SFT and RL training pipeline, and they get better at it. And if you don't have that textual instruction, the task is so hard, they don't get better at it. But with the textual instruction, they get better, so they can solve the task and they can learn to solve it. And then later in the training and that fine-tuning or RL, you start dropping out pieces of the instruction. Okay, so there's instruction still, but it's like with dropout. So the model in that stage learns, hey, the instruction is sometimes there, sometimes it's incomplete, so I better not rely on it. And it builds internal capability. I mean, we haven't done a mechanistic study, but it builds internal capability. And then when you do complete dropout, it still continues to work. Okay, so now the model that we're trying to draw is, from its internal parametric memory, it's looked at all these texts, so it has that behaviors, and then it learns to apply those behaviors. Okay, so we're trying to model that kind of process. Okay, concluding thoughts. They show sophisticated metacognition, and I'd love to hear your feedback and your comments on this. Using skill taxonomies can accelerate improved learning and also in context solving. Bigger models have higher metacognition. That's what we found generally. And it took us like a year of thinking and tinkering to figure out how to make it work for small models. I think it could be very important for AI safety and alignment, and could potentially be stronger than constitutional AI. Those of you who know about this constitutional AI framework, at least the original one was a fairly short constitution of behavior. These days, one here is the constitution is much longer, so that's basically closer to skills. And in general, it seems like Anthropic is very much on the similar skills kind of path. Okay, thank you very much. Questions? Sure. Okay, somebody who hasn't, yeah, sure.
I'm curious if you have an intuition as to what mechanism is happening here. Like for the skills, are they like different circuits are conforming to form this new generalization of metacognition?
We're working on that now, yeah.
Do you have
So,
like
almost certainly there's a circuit for the skill. Has to be.
okay,
Right?
so I see.
The question is whether we can find it. Yeah, so we are, as you can imagine, doing synthetic tasks, which we don't think appear in the training data. And there are skills and there are skill mix. So you combine skills. And we're just seeing how that emerges and compositional ability emerges. Those are very interesting. I think one paper just is on archive and another one is coming out soon. And so now that is done. And now we're going to dissect those circuits, those LLMs, and see where it lives. Thanks. Another question in the back? Or okay. Oh, wait. Yeah, sure. Go ahead. Okay, go ahead.
Super interesting talk. So my comments are just in the spirit of discussion. So let me give you an example, and I'm curious what you think. So when children learn to read, a part of their visual cortex starts to become selective for visual word forms. It's called the visual word pairs. That's an area that didn't exist, didn't have that functional selectivity when they were born, and it develops over the course. That's a literal example of repurposing neural circuitry for learning a new skill. But no human has introspective access into how they recognize visual word forms. So that metacognitively, at least in the way that cognitive scientists would typically talk about metacognition, there's no metacognitive reasoning about visual word form recognition, right? So I'm just trying to square that with how you're talking about metacognition. It seems quite different, right?
Okay. So the question was, like recognizing visual word forms. It's a skill that you acquire as a small kid, but the claim is that we wouldn't call it that. But
it's a skill, definitely a skill, but it's not metacognitive.
Oh, yeah. No. Metacognition is, are you aware of that skill?
You're aware that you have the skill, but you can't explain how you recognize it.
No.
Right. But it's
There's
an example.
nowhere in this we are saying we explain where, except at the end, all the speculation about that there are circuits. Yeah. No, yeah. So that's an open question. Yeah.
But the difference is that in the human visual cortex that I learned from UC Berkeley and UCSF Department of Ophthalmology, and also here we have the neural development in the department at Harvard main campus. And the system is different from this one because they have a built-in growing, expensive element, so they can learn over time.
This is humans.
Yeah, this is human. So that one, when you talk about the repurposing, we can learn from the industry and also the biomedical world because the FDA, they have the Metro holding system, which built in a system organ class, also like the taxonomy.
Oh, so yeah, the taxonomies exist in all kinds of fields, like for many, like decision trees and all that kind of stuff. Yeah.
I wonder whether you do any life science paper using the same platform.
Yeah, I'm not an expert on that, but it's a good idea. And
the Meta AI, they having expanding a group, they get all the medical expertise to come together as a subject matter expert, to revise this, that the data set depend on what data you input, from a group of the subject matter expert people in the community. And people are complaining when using the AI, I can easily alter it or modify it, it come back is very elementary, rudimentary.
This is all human skills. Is that what you're talking about?
Yeah, but we use the AI system and the
Oh, they're using AI to come up with this?
AI
Yeah. Okay.
But so the customer, they use the Meta AI to interrogate some type of project.
Yeah.
And when it come back, oh, if you are expert, see that it's Mickey Mouse. It's not very useful. That's why you need to get to hire a group of subject matter expert for each modality, whether math or learning or city planning or taxation or CVS medications, that kind of things. And I wonder maybe we need a life science, data set, to do the same thing, just use the same technology platform. To see how the metacognition can improve the performance.
Yeah.
Personally, can you use it for cell diagnosis?
Possibly.
Yeah, I put down all my symptoms, or I get a cancer, or I don't have a cancer.
So yeah, so I think there are already such things, right? But this could be a more interpretable, right? Like it can maybe this could be more interpretable, right? Instead of just getting an answer, oh, 90% chance of cancer in this X-ray, like a little bit more interpretability
Yeah,
and maybe reliability.
but you also mentioned about, earlier the agentic AI. So agentic AI is a multiple, and embrace the.
Maybe we should take more questions. Yeah. Other questions? Yes.
I was thinking about this way of like self-distilling the output of the model. I'm wondering if there's a theoretical limit to which you can self-distill the outputs, the variety of outputs and diversity of outputs using this, or
I think there'll be a limit. Yeah.
for example, for like vision language generation, like these models, they're horrible. They run into these loops of generating the same type of bad quality images. Maybe.
No, I don't think this will get you to super intelligence or anything. No, just it's a way path to improvement and an idea that probably will be useful. But yeah.
Yeah, so you mentioned before that acquiring the skill is different from understanding the skill. You have an intuition about how the
Knowing about the skill is different from having the skill.
knowing about the skill.
Yes.
You have an intuition about whether there are separate mechanisms or is it the same mechanism that allows the model to recognize that some tasks need a specific mechanism and actually applying the same mechanism to solve the task.
I see. Yeah, the question is like, what's my intuition about whether it's the same circuit or process that comes up with the name of the skill needed and actually applying the skill? Probably different, my guess. No, not completely different. Yeah, so hard to say. There's probably some talk between those circuits, right? Because when this one fires, that circuit fires and you apply that skill maybe. Like if you actually know, I better apply the skill, then probably it fires some circuit and you start applying it. Sham.
Yeah, maybe just going back to this question of self improvement and sort of our earlier discussion too. So what's your, having done this for a while, how are you thinking about the ability for these models to improve themselves? And one thing is that you didn't really talk about these models as say like generating computation either. So
Okay, so some of the SFT experiments is a weak form of self-improvement, right? Generate its own data and it improves itself. So you want.
Yeah, how are you thinking about just sort of self-improvement
in general?
Yeah, or just in light of like these ideas, because there's a question of like, do you need a more powerful teacher for some of these things? And how do you think about it?
No, so it also works in all the settings, self-improvement, like, so a powerful teacher helps. Were we talking about this over lunch? So yeah, so I think this PDR idea, the more sophisticated inference, right? Like the parallel. I think that's a very powerful idea. It's in some sense more powerful than RL because you are not relying on independent generations, but you're combining them. And in context, you can get improvement. So that seems like a potential ingredient for self-improvement. Like I'm thinking along those lines. Was another question back? Yeah.
So sort of going back to the question that the gentleman first asked, if you were to try to apply these ideas to a completely new domain how would you know what your set of skills are? Do you have a process for how you can develop that?
So remember instruction following. Skills of a chatbot. That was one of my examples.
Into need like a go right to come up with the.
Oh wait, are you talking about self-improvement now or?
Yes.
Only self-improvement? Yeah, for that, I think the only thing that's most relevant is the pipeline, what I told Sham, like the tree-based aggregation. That works for basically any task, not just Amy. Which makes sense, right?
Should wrap up and thanks Sanjeev again.